Hey, this is Kenneth, and today I'm going to be talking to you about orthogonal frequency division multiplexing. Orthogonal frequency division multiplexing is a multiple access modulation scheme used to allow multiple stations or one station to share a limited amount of bandwidth. Going back to the traditional channelized system that most people are used to, when you have multiple stations that need to communicate to each other, you allocate each one a fixed frequency that's far enough apart from each other that they don't interfere with each other. The problem is that it means that you have the high overhead that you need to administrate all these fixed frequencies, which are very limited in number due to their wide spacing. And you also then have the problem that if one single frequency becomes useless due to either active malicious interference or selective fading or any of a multitude of other reasons, that one station loses all service. Orthogonal frequency division multiplex instead takes what would normally be one large carrier and spreads it over a number of smaller carriers, like so. Then if another station can come in like this. This is hugely integral to LTE and most modern high bandwidth cell phone networks, in addition to a multitude of other modulation systems. The advantages here is that now if you suddenly have selective fading at one specific frequency, the station still has other useful channels with which it can still convey the information over. Of course, if you didn't have any error correcting codes, you would lose 10% or 5% or 20% of your data if you lose one of your carriers. But by taking a smaller number and spreading it out so that you have additional bits that you can then reinterpret the ones that you lose with, which is called forward error correcting, you can actually continue to operate at a reduced rate or reduced quality with the selective fading. The selective fading is a very big deal. How selective fading happens is that if you have one station that's transmitting, like this, and you have a single antenna that is listening for it over here, ideally, the radio signal goes straight there. Unfortunately, this would require line of sight from everything to everything, and the Earth is concave and not convex, which is rather inconvenient and makes this non-feasible. Then, if you have a building over here, so here's our building, and the signal bounces off of it and destructively interferes with itself here, suddenly we don't hear that one frequency. This is a function of the wavelength, and so at different wavelengths, the critical distances between this station and the building and the receiver are different, which means that in the frequency domain, as you're moving along in physical space, you would see, here's time, you would see this fading move across a wide band of frequencies. And so if you have a carrier here, let's switch colors. So if you have a carrier here, carrier here, carrier here, carrier here, carrier here, carrier here, you can see that for a short period of time, each one of them is blown out for a short period of time by this selective fading. By taking what would normally be one wide frequency that would be useless throughout all of this and breaking it into many narrower frequencies, you can cut your losses by the fact that only one of your carriers gets blown out at a time by this drifting fading or drifting interference. This is also very advantageous when you have multiple stations. So here's one station, here's a second station, here's a third station, and then you have a base station that's receiving them. You can have the base station allocate certain fractions. So if this one says, I only need 10% of the channel bandwidth, and this one only needs 20% of the channel bandwidth, and this one needs 40% of the channel bandwidth, you can sit here and take the first 10% say it's 5 carriers, give it to the first, give it to the first station. And then the next 10 carriers, give that to the second station. And then the next, that's going to be like 20 carriers here. Lots and lots of carriers, give that to station 3. In LTE, this sub-allocation of bandwidth is actually done on a millisecond by millisecond basis, which lets it very dynamically allocate what is a fixed bandwidth between any number of stations that it needs to. Unfortunately, OFDM has a few issues when it comes to actually implementing the receivers and transmitters. On the transmitting side, since you're using all these different frequencies, which need to be orthogonal to each other, they tend to not have a very good correlation with each other. Which means that at some moment that when you're unlucky, all three of them, all of your carriers can happen to be positive or negative, and the output, which is going to be a mixture of all of them, suddenly for that one moment happens to go to an unbelievably high value compared to the rest of it. And this hurts what's called the peak to average ratio. The peak to average ratio is important because you have to build your power amplifier to be able to transmit the peak power that you ever have to put out through the modulation. But the effective power that you get to put through the system is only the average. And so if your peak to average ratio is very, very large, you have to have a very powerful PA that most of the time is doing almost nothing. OFDM is very prone to this since you are transmitting multiple different signals at the same time. For example, if you were just doing quadrature QPSK, as you're modulating it, the amplitude never changes, it's just that the phase changes. But since you're modulating each one of these carriers in some way, be it BPSK or QPSK or some multiple QAM, and then summing all of these carriers together, the output can be non-ideal like this. And there's a multitude of different ways that if you very carefully code it, or by having different combinations of these carriers, you can reduce this and improve the power to average ratio, but it's an intrinsic flaw in the system. An advantage of OFDM, though, is the fact that since you are taking what would normally be a very, very fast data rate, so normally you would have to have one very wide carrier that has a very high symbol rate, and breaking it into lots of smaller carriers. Each one of those carriers only has to transmit 1 over n amount of data, which means that the symbol rate is n times as long. The fact that the symbol rate lasts longer means that where in the old system you would have to have each symbol like this. So if each one of these was a different symbol in time, on the new system, on OFDM, you instead have many symbols that last longer in time. This is important since in a real-life propagation scenario, the transitions between one symbol and the next tends to get a little blurry. This is due to multipath interference, this is due to Doppler, this is due to changes in propagation characteristics, changes in polarization. This middle part gets messed up. When you have lots of very short symbols like this, and the transition between them gets a little messed up, you can lose complete symbols. By having many more longer symbols, the inter-symbol interference in the middle here becomes a negligible fraction of your symbol rate and allows OFDM to be more robust to this phase shift or phase noise or frequency error interference caused by each of these, which causes this blurring. So this is kind of giving you a quick little introduction to OFDM, or orthogonal frequency division multiplexing. Thanks for watching.